Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're talking about 2.8. This is all about inverse functions. Inverse functions take the output of the original function as inputs and outputs them as the inputs of the original. That might sound really, really weird, and that would be fair. But what an inverse does is it undoes or reverses what the original function is doing. Okay? For example, if you have a function that is x plus 3, well, its inverse would kind of be the opposite, where you'd have x minus 3. Those are both very basic examples, but they undo each other, they reverse each other. Ideas with functions, though, there's a bunch of random things to note. One thing is not all functions have inverses. We'll talk about that in just a moment. Graphs of inverses are symmetrical over the line y equals x. And for inverses, every coordinate of the original, the inverse function has the coordinate ba. So if you have a coordinate a comma b, the inverse is b comma a. Notice those are just switched, right? The coordinates, the input and the output, the x and the y, are just flipped for the inverse. Inverse functions are also one-to-one. Well, there's some ideas here that we don't necessarily know or have talked about recently, so let's break some of these ideas down. Let's talk about what's called the vertical line test as well as the horizontal line test. The vertical line test is a method used to determine if something is a function. Okay, so is something a function? Question mark. Well, you have a vertical line. Let's draw a vertical line. I'm going to do it in yellow. Here's my vertical line. And what you do with that line is you take whatever it is and you want to move it. And you move it over whatever line you're looking at. For example, notice it's over this kind of 1/3 or cube root graph. And notice no matter where I draw this line, it will only ever touch this cube root function once. If I draw it there, it touches once. If I move it here, it's still only touching the graph once. If you continue to move it to different spots, it only ever touches the function once. The same thing would be true if you do that to a quadratic. A quadratic is a function, it only touches once. You try and move it again, and it still touches once no matter where you draw this line. Something that is not a function then, so both these were functions, yes and yes, they passed the vertical line test. Something that is not a function though is a circle. For example, if you draw a circle and you have your vertical line, notice it touches twice. That is not a function because it's touching more than once. Well, realize if you use a vertical line test, that does tell you whether something's a function, but it doesn't tell you whether that function has an inverse. Again, not all functions have inverses. A horizontal line test tells you whether something is one-to-one. What that means is for every singular input, for every x value, there is only one singular y value. Well, let's see what that may look like here. If I draw a horizontal line, it's the same idea. You want to see if it crosses once or more than once as you move that line around. And with this function, we would notice that it's still only crossing once, no matter where you end up moving your horizontal line. That does pass the horizontal line test. That is a one-to-one function. If something is one-to-one, it does have an inverse. If you take something like a quadratic, though, there might be cases that have inverses, or it will have an inverse, but that inverse will not be an inverse function. If you were to take the inverse of this function here, what you would find is something that looks like this. And notice that yellow line there would not pass a vertical line test and would not be a function. Okay, that's just one thing to note. Let's redraw our diagram. So if I use a horizontal line, that will prove to me what we just showed. It will tell me that because this horizontal line touches more than once, it is not one-to-one, and therefore its inverse will not be a function. If that's the case, one thing you could do is just restrict your domain. You might change it so your function is only part of it. For example, something like that, where you're just looking at the x values less than 0. And now it would pass your horizontal line and would have an inverse function. Okay? So you can restrict domains on functions that do not have inverses or that are not one-to-one. A circle as well would not pass. It was not a function originally, and it will not have an inverse that is a function. Okay, so just some ideas there with the different line tests, horizontal and vertical. Let's start applying ideas of inverses though. One thing we said is if you have a coordinate on an original function, right? These different points here maybe. And if you take their actual coordinates, for example, -5, 2 and -3, 0 and 0, 3, 3, -3 and 5, -2. Well, if you were to plot those coordinates for the inverse, well, we said that one thing inverses do is they switch the coordinates from AB to BA. So if I were to draw these then, maybe I take this first coordinate, -5, 2. That inverse would be 2, -5. Sorry, 2, -5. Which is this point way down here. And you could do that for each of these. You could change the coordinate to 0, -3. You could change the coordinate from 0, 3 to now 3, 0. You could continue to change the coordinates from 3, -3 to -3, +3, and from 5, -2 to -2, 5. This gives you your inverse graph, which looks something like this. The other thing we said is we talked about how inverse functions were symmetrical over the y equals x line. Notice that is true. We just simply mirrored the blue line across this axis to now give us our inverse function as well. Now you can see some of those ideas and properties we talked about. The last thing we should talk about for inverses, though, is just finding an actual inverse function. Well, what we said is inverse functions switch your x and your y. Well, remember your output f of x is just the same thing as y, just in a different notation. So one thing you might do is just rewrite the original function. But in order to find the inverse function, then, you would need to switch your x and your y's. So if there's a y, it changes to x. If there's an x, it changes to y. And now we get something like this. But we don't normally write functions as the input equals. It's usually the output that is by itself. So we'd have to start to solve for y. Well, if there's a y on the denominator, you're never going to get that y by itself unless you move it out of the denominator. In order to do that, we'd have to multiply by the entire denominator, y plus 3. That gets rid of any fractions that we may have had. Well, what I notice is there's this y that's trapped on the inside of the parentheses. So let's make it so it's no longer in parentheses. Okay, we just distributed the x to the inside to do that. Well, the next thing I notice is I have these different y's on two different sides. So I'm going to collect all of the y's on one side and all of the other terms on the other side, giving me now a function like this, xy minus y equals -3x minus 2. Well, the reason I would do that is now this left side has all of the different y's. So one thing I might look to do then is take the y's out and see what's left over. In other words, you could factor a y out leaving us with x minus 1. But when I do that, now this is just y times something. So if I want y by itself, I could divide that entire component over. I could divide this entire thing by x minus 1 and end up getting the inverse function. We were in function notation originally with f of x. The inverse of f of x is just shown with this f to the negative 1, where this is our inverse function. I urge you to graph those two functions, the original and the inverse, on Desmos and prove and show to yourself that they are symmetrical over the line we found, over y equals x. Let's look at another example finding the inverse. Process is still the same. You still need to switch your x and your y. So now we would have x equals 10, quantity y plus 3 to the 1/2 over 9. And we need to get the y by itself. So y is just trapped inside a bunch of things. So one thing a lot of people like to do is distribute the 10 to the inside. But you don't have to do that. Instead of distributing, why don't you do the opposite? The opposite of distribution or multiplying is division. That will just move components to the other side faster. It will save you steps. Before I can deal with the y on the inside of the parentheses, we need to figure out what's on the outside and get rid of it. So maybe I now multiply by 9 on both sides. That gets rid of the 9 on the right, leaving me with just y plus 3 to the 1/2. Before I can move anything inside the parentheses, you need to get rid of whatever's causing the parentheses. That is the 1/2. Well, if you're raising something to the 1/2, that's the square root, basically. To get rid of a square root, you could square something. So in other words, we square both sides. That would cancel the square root on the right, or the 1/2 power, and the entire left thing would now be squared. You could end up simplifying this, getting the y by itself, subtracting the 3 over, getting 9x over 10 quantity squared equals minus 3 equals y. Notice the 3 was not squared. And you could change this if you want to be 81x squared over 100. You don't have to do that. And that is our inverse function, where the original was g. Again, inverse is shown with the negative 1. You don't say g to the negative 1, though. You just say the inverse of g. There is a bunch of different stuff about inverses, about functions, one-to-one, all of sorts of things there for our 2.8 notes. Thanks for watching.